Hey everybody, so this is our Test 3 review for spring of 2022. Just in general, since Test 2 we've covered chapters 7 and 9 in Purcell and Morin. That ray optics info that I put at the bottom of our class website with the extra credit homework, that is extra credit, okay? And so that's not going to be covered on the final or on Test 3, so just don't worry about that for this test. The format of the test will be the same as the previous test. No new surprises. It'll be 4 long answer questions probably. So bring a 3-inch by 5-inch note card as an equation sheet. And I'll give you that same constants sheet that I've been giving you on previous tests, so you won't have to waste your note card space on fundamental constants or on vector calculus stuff. Remember that I don't really care what the number answer is so much for numerical based questions or whatever. I just want to make sure that you understand the physics. And so to that end, really show your work for full credit because that's what I care about. So your test is on Tuesday, April 26th in class. That's the last day of class also. The official last day of class is Wednesday, but of course we don't have class on Wednesdays, so there you go. Your final exam is going to be May 5th at 8 a.m. Now, I'm not going to post a separate review for the final exams because I've been recording all the test reviews. So this is your Test 3 review. Test 1 and 2 reviews are already posted, and you can watch those to review for the final exam. Do check your email. I might post some practice final exam questions, so you can check your email for that. But I'm not going to post another recorded video lecture. Okay, so right into the material. First of all, we covered Faraday's law, and it's Faraday's law of induction, and it states that the electromotive force induced in a circuit is directly proportional to the time rate of change of that magnetic flux through the circuit. Now, first, remember that electromotive force is a voltage, not a force, okay? It's just an old-timey term for a voltage. So the EMF, which is that curly E, is equal to minus N d phi b dt. So here N is the number of turns, or the number of turns in a loop. And then phi b is the magnetic flux that we first defined flux when we started talking about Gauss's law. So remember that. It's the integral of b dot dA. So it's the time rate of change of the magnetic flux. So if you expand that out, remember that we derived this in class, that the electromotive force induced from Faraday's law is equal to the line integral of E dot ds, okay, no minus sign here, E dot ds, and that's equal to minus N d phi b dt, which is minus N times the time derivative ddt of the integral of b dot dA. Now, we put this also in differential form, and if you do it in differential form, the curl of the electric field is equal to the negative time rate of change of the magnetic field. So del cross E is minus partial B with respect to T. So that's Faraday's law. So remember that you can induce an EMF by changing the magnitude of the magnetic field. So for example, if you have a current running through a solenoid and the current's changing with time, then the magnetic field in the solenoid's changing with time. So that's one way to change a magnetic field, is to change the magnitude of it. You could also, all you have to do is change the flux. Change the area enclosed by the loop. That was kind of our motional EMF thing. You can change the angle between the magnetic field and the normal to the loop. So you can have a magnetic field and then a loop inside of it rotating, for example, or any combination of the above. So any of those will induce an EMF for you. Now remember that the minus sign in Faraday's law is also known as Lenz's law. And Lenz's law says that the induced current in a loop is the direction that creates a magnetic field that opposes the change in the magnetic flux through the area enclosed by that loop. So in other words, the induced current from the electromotive force tends to keep the original magnetic flux through the circuit from changing. So it's that minus sign. Remember, things don't want to change, they want to stay the same, and so it's just trying to maintain. So it'll induce an EMF that will oppose the change in flux. Okay, we covered inductance. So magnetic fields are generated that oppose the change of magnetic flux via a back EMF, as it's called. And this induced EMF is always proportional to the time rate of change of the current. So we express that mathematically as back EMF is equal to minus L di dt, where L is a constant of proportionality that's called the inductance of the coil. And it depends only on the geometry of the coil and other physical characteristics, okay? So in that way, it's kind of like a capacitance. Now, you can also have mutual inductance. So this is the equation for self-inductance. Remember, self-inductance is symbolized by an L. But you can also have one coil causing a back EMF in another nearby coil. That's actually what Faraday's original experiments were. And so if that happens, then it's mutual inductance. So remember that the expression to find the self-inductance of an object L was equal to N times the magnetic flux phi B divided by the current through it. And this is a measure of the opposition to a change in the current. The SI unit of the inductance is the Henry, and 1 Henry is 1 volt second per amp. I know it's a little strange unit, but there you have it. Now in mutual inductance, here we have coil 1 and coil 2. We had a current that was induced, or that started in coil 1, and that created a magnetic field which passed through coil 2, and that changing magnetic flux through coil 2 induces an EMF in coil 2. So like I said, that was Faraday's original experiment, kind of. So mathematically, we can express that as the EMF induced in coil 2, or E sub 2, is equal to minus N2 times d phi 1 dt, okay? Now, that is the same as saying that there's a mutual inductance between the two, which we symbolize with big M, and that back EMF is proportional to the mutual inductance and the time rate of change in the current. So mathematically, that's minus M12 di1 dt. So if there's a current in coil 2, then there's a mutual inductance M21. It goes both ways. And remember that the mutual inductance M12 is going to equal M21. So you figure out whichever one is easier, right? And that's the one that you're going to do. Okay, the general expression for the mutual inductance M12 of coil 2 with respect to coil 1 is M12 is equal to N2 times phi 12 divided by I1. Now remember, you're dividing out by that I, which cancel out with the dependence in the current on the top. You shouldn't end up with a current at the end of your expression, okay? So the mutual inductance is going to depend on the geometry of both circuits and on their orientation with respect to one another, but not the current, okay? So here's how to find the self or mutual inductance of some coils. So first, you find the magnetic field as a function of current for the objects. Okay, if you don't know it already, usually Ampere's law is the easiest. But for example, on the test, if you remember what the magnetic field of a solenoid is, you can totally use that, and I'm going to be okay with it. All right, number 2, you find the magnetic flux for the object using the magnetic field that you found in part 1. Okay. Number 3, you find the self-inductance using the equation L is equal to N phi over I, or the mutual inductance equation, which I gave here, M12 is equal to N2 phi 12 over I1. So either one of those expressions, depending on whether you're trying to find the self or mutual inductance. Then you should be able to cancel stuff out and end up with an expression for L or M. When you're finished, you should have no current. You should not have current. Sorry, that should be a not. Have current in your expression. And that's because, much like capacitance, it's a function of physical characteristics of the inductors, but not on the current. Okay, so we've defined inductance L, and you might know, of course, that we purposefully put inductors in circuits for various applications. And so if you do have an inductor in your circuit, we symbolize it with an L, and we call it an inductor. And the circuit symbol is that curly line, not the jagged line, that's a resistor, but the curly line as shown here. So what we're going to do for our circuit problems is assume that the inductance of the rest of the circuit is small with respect to the inductance of an inductor if you place it in the circuit. But just remember that it's true that even without an inductor in the circuit, every circuit is going to have some self-inductance. So that's something that you might need to think about later if you end up in an experimental lab or in industry. So we did RL circuits in class. And RL circuits are when you have a resistor and an inductor that may or may not be connected to a battery. Okay? So here we show an RL circuit. You have a battery with an EMF and a couple of switches and then a resistor and an inductor. Let's first assume that you close switch S1 and switch S2 is in position A. Okay? And so that means that the battery is in series with the resistor and the inductor. So once you first close that switch S1, initially there's no current running through the circuit at all. Okay? So there's no flux through the inductor, right? No magnetic flux through that inductor. And the inductor would like to keep it that way, right? It doesn't like change. And so what it will do is introduce a back EMF to oppose that change, all right? Now that back EMF will cause a voltage drop across that inductor as you walk around that little circuit clockwise, right? So we derived the expression for a current flowing through this kind of RL circuit in class. And it's shown here. The current as a function of time is equal to the EMF of the battery divided by the resistance of the resistor R times 1 minus e to the minus t over tau. Now here t is time, but tau is the time constant of the circuit. And the time constant of the circuit will be equal to L over R, where L is in henries and R is in ohms. Now, physically, the time constant is the time that's required for the current to reach about 63% of its maximum value, okay? So what will happen is, when you first close the switch, there'll be a back EMF through the inductor that opposes that current flow through the circuit. And it will not allow any current initially. So the initial current when the switch closes will be 0 because the inductor is generating so much back EMF. But then as time goes on, okay, the current will increase exponentially. And then eventually, once it reaches its steady state, it'll be like the inductor's not even there. It's acting just like a straight wire, okay? Because it's reached that steady state and there's no more time rate of change of the current through the inductor, okay? So then there's no voltage drop across the inductor. Now, let's say instead that you have a nice current, nice steady state current flowing through that inductor, okay? And then at that time, when you've got that steady state current, you move the switch S2 to position B. Then, for a brief amount of time at least, the inductor will act as the power source for the circuit. It'll generate a back EMF to oppose the loss of the flux, magnetic flux, through that inductor, and it'll act as the power source. So initially, it will try to keep the current flowing at the value that it was when it reached the steady state. So initially, the current will be equal to the EMF of the battery over R, okay, initially. And then, as time goes on, that current will exponentially decay away, okay? And so, without a battery, it will be, the current will decay exponentially. You'll have I naught e to the minus RT over L, or e to the minus t over tau. And that I naught will be the EMF of the battery over R here, okay? So that's what's happening there. Okay, so you've got exponential decay for currents, or exponential functions, I guess, for currents in RL circuits. And this is kind of similar to circuits with capacitors. A lot of parallels can be drawn, pardon the pun. Now, remember that if you combine inductors in a circuit, it obeys similar equations to the combination of resistors in circuits. If you have multiple resistors or inductors in series, they add, and in parallel, you're going to take the reciprocal and add those to get the reciprocal of the total inductance. Also remember that we derived the equation for the energy stored in an inductor. Remember that fields store energy. That's what fields do. And so the magnetic field inside the inductor is what is storing that energy, much like the electric field in a capacitor is what's storing the energy. Okay? And you can find an expression for the potential energy stored in the magnetic field of an inductor. It's 1/2 Li squared, where L is the inductance and I is the current. Okay, so fields store energy. Electric and magnetic fields both store energy. In fact, we're going to review the expressions for both of those there. Remember that the total energy stored in a field is going to be proportional to the volume that the field occupies, of course. And so what we've done is we've gotten an expression for what we call an energy density, which is an energy per unit volume. And the energy density expression for magnetic and for electric fields looks similar. And here they are. The magnetic field energy density is 1/2 B squared over mu naught, where B is the magnetic field strength in the region. And U sub E is 1/2 epsilon naught E squared, where E is the electric field strength in the region. And remember that mu naught and epsilon naught are the permeability and permittivity of free space, those fundamental constants respectively. Okay, Ampere-Maxwell law. Okay, so that was Faraday's law and all that good stuff. Here we go, Ampere-Maxwell law. Remember, we've already talked about Ampere's law. If you have an enclosed current, right, then you can write an expression for the magnetic field due to that enclosed current. And that is the integral about the closed loop of B dot ds is equal to mu naught I enclosed. But that ignores the contribution that a changing electric field would have to that expression. And remember that we were first alerted to this problem with the capacitor plates. In other words, if this expression, this mu naught I enclosed expression, would not predict a magnetic field in between a charging capacitor plate, for example. But if you were to measure it there, you would find a magnetic field there. And so to account for that, we talk about the so-called displacement current that Maxwell introduced. And so now we have the Ampere-Maxwell law, which includes the contribution of any enclosed currents and also any changing electric fields that might be present. And so the full expression in integral form is the integral about the closed loop of B dot ds is equal to mu naught I enclosed plus mu naught epsilon naught times d phi e dt, where phi sub e here is the electric flux, the integral of E dot dA. And you can take that second term in the expression, that epsilon naught d phi e dt, and call it the so-called displacement current I sub d. And so you could write that the integral about the closed loop of B dot ds is equal to mu naught I enclosed plus I displacement. Now, in differential form, the Ampere-Maxwell law is expressed as del cross B is equal to mu naught J plus mu naught epsilon naught partial of E with respect to time. Okay? So those are the two forms of the Ampere-Maxwell law. Now remember that once this law had been written out, Maxwell then did his famous derivation, where he showed that the speed at which electromagnetic waves travel is the speed of light, and that the speed of light can be written in terms of other fundamental constants, mu naught, epsilon naught. Okay? So this result led Maxwell to predict that light waves were a form of electromagnetic radiation, and he showed that light can exist at any frequency and not just visible light frequencies. This achievement was so huge that we now call those four fundamental equations of electricity and magnetism: Gauss's law for magnetism, Gauss's law for electric fields, Faraday's law, and the Ampere-Maxwell law. We call them all Maxwell's equations in his honor. And remember that those four fundamental equations, combined with the Lorentz force law, are pretty much everything that we know about classical electricity and magnetism. So Maxwell knew that light was the wave. To do the derivation, remember, we assumed that fields were real things, that they could exist independently of the source charge and away from the source charge in empty space. And then we said empty space means no source charges or source currents. Q and I are 0. And then we went through that full derivation. Okay, I'm not going to repeat it here in the review. All right, it's online if you want to look at it again. But one of the main conclusions, our climax, if you will, of that derivation was that you could see that in SI units, the speed of light c is 1 over the square root of mu naught times epsilon naught. Okay? And then, of course, the speed of light in a medium would be 1 over the square root of mu epsilon, where mu and epsilon are the permeability and permittivity for that medium. We also showed, as a result of this derivation, that the magnetic field strength, B, was equal to the electric field strength, E, divided by the speed of light. Okay? So, and then finally we showed that a light wave, you might be able to picture it like this if it were a plane polarized wave. Here we have the electric field in blue, and it's oscillating in time sinusoidally. And that changing field in time, that changing electric field, induces a magnetic field, which is perpendicular to it and the direction of propagation. Okay? And so the magnetic field induces an electric field, the electric field induces a magnetic field. This is why we call it a self-propagating wave. All right? So light, or electromagnetic radiation, is an transverse self-propagating wave. All right, we also defined the Poynting vector. The Poynting vector S is 1 over mu naught times E cross B. Remember that the Poynting vector points in the direction of propagation of the wave. Okay? if you write it this way, it's of course time dependent because your electric and magnetic field are time dependent, okay? And so the magnitude of the pointing vector will vary in time, but the magnitude of the pointing vector reaches a max at the same instant that E and B reaches its max. So if you do the time average of the pointing vector and average over one or more cycles, then what you'll get is the wave intensity, okay? So the wave intensity is the time average of the pointing vector, all right? Remember, the definition of an intensity is a power divided by an area, okay? So intensity is power over area. So in terms of the intensity, I is equal to the average value of the pointing vector, which is equal to C B naught squared over 2 mu naught. Okay, and then you could also write that in terms of E naught. Remember that B naught here is the max value of your magnetic field oscillation. So it's like B is equal to B naught sine kx minus omega t. So that B naught, the one out front of the sine function, okay? And that the time average value of the pointing vector, the intensity, is also equal to the speed of light times the average energy density. Now, the average energy density here is the sum of the energy density from the electric and the magnetic field. So that would be C times UE plus UB, okay? All right. Finally, we covered the polarization of light waves. Remember that the direction of polarization of an individual wave is defined to be the direction in which the electric field is oscillating. So in this picture, we see a plane polarized electromagnetic wave. The polarization direction is in the Y, okay? Now, it doesn't have to be linearly polarized like it is here. It can be circularly polarized, which means that the electric field vector oscillates and moves around in time in a counterclockwise or a clockwise fashion, okay? All right, now, how do we polarize light? Well, light can be polarized through many of its interactions with matter. So it can be polarized through scattering, reflection, refraction. All of these processes can polarize light. Now, if you have a polarizer, okay, remember we talked about polarizers and did some demos in class, then what the polarizer does is it selects a certain orientation of the polarization. The intensity of a polarized beam transmitted through a second polarizing sheet varies as the cosine squared of the angle in between the two polarizers. And so let's say that you have some intensity I max of an already polarized beam that's incident on another polarizer that is oriented at an angle theta, okay, to the original angle of polarization. Then you'll have I is equal to I max cosine squared theta. And that's known as Malice's law, or the law of Malice, okay? Not the mean one, not M-A-L-I-C-E, but M-A-L-U-S, okay? Now, if you have initially unpolarized light incident on a polarizer, then, as we showed in class, that will cut the intensity of the initial beam by half, all right? Okay, that's all she wrote. That's a nice review, nice overview. Don't forget to work the practice test, look over your old homeworks, and work extra problems to best study for your test. And let me know if you have any questions, and I'll see you in class.